This is a picture of a graph. Although it undoubtedly looks like a mess, the blue dots are actually the nodes, the lines are the edges connecting them. And here's a special set of nodes that we have highlighted in magenta. There is a famous algorithm called the spectral embedding that is designed to make a better picture of a graph. It works based on turning each edge into something like a spring, then finding the lowest energy state of the springs. Let's look at the spectral embedding. So this looks very different from the previous embedding, and I think we can all read off the word equator among the magenta nodes. Well, secret's out. Here's the original graph, and I planted the word equator into it. Except that is not the spectral embedding. Here's what we saw, and here is the actual spectral embedding. This picture that I originally showed is what we call a log PageRank embedding. It uses Google's PageRank algorithm, the log function, and an SVD to come up with pictures that are really similar to spectral embeddings. That is super uncanny. At least that's what we thought when we first saw this. I mean, what has a ranking algorithm got to do with spectral embedding? We noticed that it was the same for a lot of other graphs as well. For example, here's the road network of the state Minnesota. The picture on the top shows spectral embedding, while the one below shows the log PageRank embedding. And here's a 5000 node graph with each node connected to 6 of its nearest neighbor, with similar embeddings. Notice the location of these brighter dots? These nodes confirm the resemblance of the embeddings. In this video, we'll talk more about this embedding procedure called the log PageRank. The first component of this procedure is the PageRank. It has been around since 1998. As a standalone algorithm, PageRank was introduced by the founders of Google. The search engine uses it to rank the web pages returned by the internet. Fundamentally, it's a random walk on a graph that occasionally restarts on a predetermined node called the seed node. Here, the blue node acts as the seed node. And the walk then travels along these green edges which are chosen at random among the edges of the current node. But every once in a while, after taking a few steps along the edges of the graph, as you can see, the walk will reset to the blue node. Such walks can be mathematically analyzed using this relation. Here P is a column stochastic random walk matrix, V is the indicator vector for the seed node, which is the blue node in this case, and X is the PageRank vector used to rank the nodes. This equation says that a random walk on this graph, starting on the blue node, will continue on the walk with probability alpha, but can teleport back to the blue node with probability 1 minus alpha. So we call alpha the teleportation probability. Google decided the value of alpha to be 0.85. So with that value and the blue node as the seed node, we get this value for X. This can then be translated into a rank like this according to the order. And when the seed node changes, the PageRank vector would change like this, which would further change the rank of the nodes. This begs the question, how do you decide about the seed node? Google was interested in which is the most important page on the web, so they had it restart at random nodes each time. This gives global importance, but they were also interested in what was important to a single person. So choosing a particular node as the seed gives a measure that is personalized to that seed, which in Google's case would be the user. Hence the name personalized PageRank. For our purpose, it can be random. As long as you have large enough population of different seed nodes, the final results don't differ that much. This is because a seed node only helps with the localization. That is, when you have different seed nodes, the random walk would visit different parts of the network. For example, here the magenta circle shows the seed node and the colors correspond to the values of X. On this 500 node graph with just 4 different seed nodes, we visit almost half of the graph. We also see that the PageRank vector effectively creates a diffusion on the network starting at the seed node. This is expected because the PageRank equation is closely related to the heat flow equation. So we can see here how the PageRank values diffuse from the seed node. That is, if we take a sufficiently high number of seed nodes, the diffusion should be able to visit most of the nodes in the graph. But here's a catch. With the same network and the same seed nodes, the diffusion on our right is able to visit many more nodes than the one on the left. This is the effect of log. The values on the left are the values of X from the PageRank equation, but on the right, the values are log of X. So what happened is, we realized we don't really care about the precise values of X. For almost all purpose, we just want to know the big differences in the PageRank scores, and that's exactly what the log transform accomplishes. Google almost never used the raw PageRank values because the log of these values enable a much more clear ranking. Okay, so that's PageRank and what the log operation does to the PageRank. But how does that generate pictures like the spectral embedding? But more importantly, if they are so similar to spectral embeddings, why not just use spectral embedding? Our paper answers both of these questions. To build some insight, this is the diffusion generated by log PageRank, while this is the diffusion generated by different powers of the matrix used for spectral embedding. That matrix is loosely related to the random walk matrix P as shown. Our paper quantifies the precise relation between the two matrices, but the resemblance shown here was the starting point. To get the embeddings, we consider a few seed nodes and stack their log PageRank vectors together. The resulting matrix is then used for its second and third left singular vectors, which correspond to the two-dimensional embedding. Remember that the seeded PageRank values are all less than 1. So the log version can be scaled such that we take SVD of a matrix of all positive numbers. Now for a matrix like that, the dominant left singular vector is very close to all ones, which doesn't tell us much. So the next two are what we call the log PageRank embedding, which gives us all these representations that are so similar to spectral embeddings. This brings us to why would you at all want to use log PageRank instead of the former? You see, there are certain cases where spectral embeddings just cannot be used for any useful inference. For example, here we are trying to visualize an artist preference network where the nodes are the artists and an edge indicates that both the artists are similarly preferred by the users. So if you can spot a faint line on the right of the white box, that is the representation created by spectral embedding. While on the right, we have the log PageRank embedding, which clearly gives a lot more information. Another form of network is the hypergraph, where we have hyperedges instead of edges that connects more than two nodes. For this kind of network, the idea of spectral embedding isn't quite clear. Here we have a contact tracing dataset in a school, where each hyperedge denotes the people who were in physical proximity of each other, and the embeddings shown by log PageRank are colored by people, both teachers and students, who belong to the same class. And we can see nodes belonging to the same class are placed close together by the log PageRank embedding, which is expected because being in the same class, they must have been in physical proximity. So we have seen that the log PageRank embeddings indeed generate inferences worth looking into. Full disclosure, these vectors don't always generate good pictures, but the log PageRank setup in our method gives you a ton of flexibility beyond just spectral embedding. In our paper on this topic, we look at conditions where we are able to prove that they will be similar in a theorem, and this QR code should take you there. So if PageRank or any other diffusion does a good job on your data, you can probably get something interesting with log PageRank. Please check out our paper at this QR for more information and cite it if you find it relevant.